So this is the Unit 5 review session for waves for college prep physics. And we have our test coming up in a couple days on Tuesday. It is now Sunday. So let me know if you have any questions and I will answer them. Really all you need to worry about that's on the test are the three I can statements, the three acquisition statements that we've seen in class. So if you just go through your review guide, your study guide, you should be fine. Now the test questions won't necessarily be just like the review questions, but they're going to be covering the same topics, and you'll require the same knowledge and background information in order to answer these questions that you are going to see on the test. So pretty much make sure that you can actually do these things. So if this says I can define wave velocity, frequency, period, and wavelength, explain the relationship between them, and solve for any variable, make sure you can do that. And so the questions in this first section of the review guide are trying to help you, well, review for that. Okay, so like I said, these are typically, on the review guide, they are lower level type questions. And as you know, on the test itself, there'll be a little bit more deeper questions to ask for you to answer that require you to know how to do this stuff. So the key is pretty helpful for this review. I mean, again, just make sure you know that the different parts of the wave. The crest is going to be the tops of all the wavelengths of all the waves here. The troughs will be the bottom parts. A wavelength is going to be letter B here. Any distance, like a full complete cycle. So it could be from the top of a crest to the top of the next crest, or it could be from, like, say here, and it just has to be a complete cycle. So it's going to go all the way up, all the way down, and here again, and that would be a wavelength. Okay, so just any you pick a spot and you go the entire distance and you're back again to that spot. So on the downhill side of this hill, all the way to the downhill side of this hill would be a wavelength. The wavelength is just the length of a wave. It doesn't matter where you measure it, as long as you measure one complete wave. So amplitude is going to be just the distance from the resting point to either the top of a crest or the bottom of a trough. And honestly, just make sure you know the difference between longitudinal and transverse. Longitudinal, remember, just go back to the PowerPoint with the animations, and the longitudinal will be also known as compression wave. There's a couple ways to say it, but longitudinal will be where if the wave is going side to side, if the wave is going from, like, say, right to left, then the little particles in the wave, in the medium, will also be going in that direction. They'll be going parallel to the direction of the wave. A transverse wave, on the other hand, if the wave is going from right to left, left to right, then the particles in the medium will be going perpendicular to that. It'll be going up and down. That's the main difference between the two. So just make sure you can do that, and make sure you're able to calculate wavelength. Like this one says, if the whole thing is 10 centimeters, what's a wavelength? Well, like I said, one wavelength is the distance from the beginning of a wave to the beginning of the next wave. So we have, if this is the beginning of the first wave, let me switch my pencil here. Actually, that was my pencil. Then the beginning of the next wave will be here, because it goes all the way up, all the way down, and back again. So there's one wave, another wave right here, and another wave right here. So there's three complete waves in this diagram. And so you just divide the 10, take the 10 centimeters, divide by 3, and that's why the answer would be 3.33. I mean, repeating. So the answer would be B there. All right, so just understand what all that is about. And like I said, if you have any questions, you guys just jump it on. Let me know, either in the chat or using the Remind app. So compression and rarefaction are two parts of the wave, of a longitudinal wave, that you should be aware of. That's compression is fairly obvious. If you think of a sound wave as the air molecules are sort of just bumping into each other, and you get this like chain reaction going down the line. Compression is where the molecules will be compressed together, or in a slinky. It's like, you know, slinky wave, the side to side one, not necessarily the ones you guys are doing in the hall, but the side to side ones, the slinky waves, the pulse going through it, the compressions where the medium is compressed. The rarefaction is the opposite of that. If something's being compressed, then that means somewhere else it needs to be stretched out. So that's all a rarefaction is, just a stretch out. These are just basic terms that you need to be familiar with. Again, if you just go to the first set of notes, you'll see all these terms and just be familiar with them. You could write them all down in your index card if you want to. Okay, we'll take care of the index card tomorrow in class on Monday. So a wavelength, just like before, would be excuse me, letter C. It's just one entire wave. It's the beginning of one wave to the beginning of the next wave. That's all it is. So look for the patterns. So otherwise, not too much else. I guess for 13, the crest, if you want to remember, let's scooch this up so you can see it. So the crest is going to be the up part, the positive part. So if you want to think of a crest as like the positives, and a trough is the part that goes down. So if you think of crest like a negative, well, if you got a 4 meter positive meeting a 1 meter negative, then your answer is going to have to be 3 meters, because you start with 4 and you subtract 1, you take 1 away. So that's what crest versus a trough is. If you think of it like the diagram up here, crest, trough. So one's positive, one's negative. That's all that is. These next few, 15 and on, up to say about 21, really just require that you understand the equations involved here. And once again, I'll put them up in a second. They're already on the OneNote. But you should be familiar with what all the letters mean and how they're all related to each other, when to multiply, when to divide. The practice problems that we did last week or 2 weeks ago will be very helpful with that. But once again, you're not going to see very many questions on the actual test that are this simple. You're going to have to just know how to use them, and like it'll be in the context of some question or some problem. So to help you out, I'll put this up just for a few minutes. These are the equations. They're not written in the best hand. I mean, my handwriting is kind of terrible, but you know, whatever. But these are them. If you want a slightly better one, more clear, I guess, it's on the OneNote. It's on the notes also, which are linked on the OneNote, but it's also directly on the OneNotes page. And you can see those equations there too. So this is definitely something you want to write down in your card, although I will have them up on the screen. This is the only thing I'm going to have on the screen on the test day. So I will have these up on the board for you to see, but that'll require you looking up, and you might just want to write it on your note card just to make things easier for you, and just have everything all self-contained like that. All right. So that all goes to, actually there's a little bit more. You know what, before I go any further, I do just want to say, like, this kind of goes without saying, but I should say it anyway since this is the review session. It's going to be super duper helpful if you're this is a second nature to know what all these letters mean. So you shouldn't have to think about the fact that capital T stands for period. I mean, if you want to write that on your note card, you certainly can, but you know, don't take it for granted that you know what these things are. So make sure you know capital T is period, the little scripty F is the frequency, velocity, and this little thing right here is the Greek letter lambda, that's wavelength. So definitely make sure you know all those things and what all those letters stand for, because you're not going to want to have to be second guessing yourself on the day of the test. All right. So, as I was saying, question 22, which material would sound not travel at all? I mean, don't forget that the whole idea of a wave, especially a mechanical wave like sound, requires a medium to travel through. It requires some matter that has molecules able to bump into each other and send that chain reaction wave through it. And so lead, sound can travel through lead, sound can travel through water, sound can definitely travel through air. But it's that empty space that sound cannot travel in. So again, just it's, you know, the vacuum of space. You're not going to have any molecules to bounce off of each other and propagate the wave or continue the wave. All right. So all that goes to, and then there's a couple more questions. We kind of touched on these again. These are just not the most important. These top ones, 23, 24, and 25. Actually, 25 kind of is, but 23 and 24, just keeping in mind that sound travels the slowest in air and it travels the fastest in solids. Okay, so it goes from slow to fast. It goes air, liquids, so gas, liquids, and then solids. All right, again, it's all in the notes, so I'm just reviewing, pointing out some things that pop out to me right now, and just making myself available if you have questions. Excuse me. The last thing is, what part of a wave determines the volume of a sound wave? If you think of volume as just the energy, okay, if you're listening to music and you turn it up, what are you doing? It's going to drain the battery faster. Why? Because it needs more energy. Because what's it doing? It's pushing harder on the air molecules. And so to do that, the energy, the volume is going to be determined by the amplitude in a wave like this, in a mechanical wave. So that's just something like, if you think about this, the lab in the hallway. I mean, when you, let's see, give me some room here. I'll just do it on the pad. When you made a wave like this, some other groups were making waves like much bigger. And just going off of the amplitude, we'll talk about frequency later, but just going by the amplitude, I mean, the height of those waves just took more energy to make. So these were the springs, the slinkies in the hall, the springs in the hall. Okay, so that's number 25 there. Just amplitude is definitely a big indicator of how much energy it takes and how much energy the wave is carrying. In fact, where's the question? I know it's here. If not, I guess I didn't know. Here, I'm gonna write this down because this is important. Waves carry energy. Okay, big note right there. That was on the notes, I think, a couple times. That's the idea. That's the whole point of waves. That's the reason that we like waves, is because it can carry energy. It can carry energy in patterns that we can use to carry information. But waves transmit energy. I shouldn't say carry, maybe so much as transmit. But if you put energy in at one end, the energy is going to travel through the medium and come out the other end, and that's what we like about waves. So all that has to do with this first part of the unit, defining wave velocity, frequency, period, and wavelength. So V, F, capital T, and that Greek letter lambda. Okay. Explain the relationship between them. In other words, it makes you know the equations, and solve for any variable. That's it. That's the whole first part of the unit. Okay, so make sure you can do that, and you'll be fine on the test. All right. Not seeing any questions, so I'm going to continue on. Reflection and refraction. So reflected just means that it bounces off at the same angle, and that's what this question number 1 is all about. I mean, we all know what reflection means. It's just, you know, make sure you're able to explain it in your own words. The law of reflection, basically, I'm going to draw it kind of, sort of. If you've got a surface like a mirror, and let's say I just draw this like little line, what we call it, like a normal line. If you have a light ray coming in, a beam of light coming in at a certain angle, call it theta, then it's going to bounce off at the same angle. Okay, so those two angles will be the same. That's the law of reflection, is the angle of incidence, the dense, is equal to the angle of reflection. And I'll just say that they're equal. So I put the diagram there, but if you want to put it into words, it's in the notes, but the angle of incidence is equal to the angle of reflection. That's the law. That's the law of reflection. Okay. Question 2. Okay, I kind of did that for number 3. So the incident ray here is number 1. The reflected ray is number 2 right here. The angle of incidence, 3. The angle of reflection, 4. And the normal line, 5. Okay. So I'll write that on the board tomorrow during our review session, just so you know that. The fun, I'm not going to do that one right now, but I mean, I let you have some fun with that and try that out yourself. Okay, basically just draw the reflection. That's it. So put a mirror on the right side of the word next to the letter fun, or next to the letter N, and what would it look like reflected? All right, draw the mirror. In fact, if you want to check yourself, just put it up against a mirror, and then you'll know. All right, what's the difference between a real and a virtual image? Again, something we kind of touched on, but might not be something that you are familiar with. So the real image, let's say you're getting ready for school in the morning. The real image would be you, like the actual you that's looking into the mirror. The virtual image is the fake you that seems to be behind the mirror. I mean, I don't know if you know this or not, but there's not actually somebody there when you're looking in the mirror. There's not, if you're standing 2 feet in front of the mirror, it looks like there's somebody 2 feet behind the mirror, but there's not, obviously. I'm just joking, but that's what the virtual image is. Like your dog or cat might not realize that there's not somebody else there, but we do. And so the real image would be the you, the person there. The virtual image is the reflected you in the mirror. Okay, refraction. So I'm gonna need some blank paper here. So if I've got some, let's call this water, and this is air. Okay, so basically what happens, and I'm gonna summarize this, is water is more dense than air. It's thicker, you could say, if you want to. So the molecules are closer together. Light has a harder time going through it. It just goes a little bit slower in the water compared to air. And so when light hits it at an angle, basically what's happening is, that's my light wave hitting it, is when the light actually hits the water, that part starts to get twisted and it twists the whole thing down. And so the light rays coming in hits the water and bends inward, okay? The same thing is going to happen, but in reverse, if a light ray leaves the water. So the light ray is coming out of the water, it hits the air, and the part that's in the air kind of speeds up a little bit, and so it bends away from the way it was going. All right. So to represent that, we have some pencil here. We draw a normal line, a perpendicular line, just to kind of give us a little reference here. I'm going to do that in both situations. Usually I draw a dotted line. And so if a light ray comes in, probably, let's get a ruler here. So if I just draw a straight line of a light ray coming in, so this is my incidence, okay, my ray of incidence. It's a light ray. It's just light. Okay, my light. Coming in at a certain angle, like I said, when it's going into water, it's going to bend inward. It's going to bend toward that. So it's going to be a much, like, for example, maybe not that much, but let me just kind of fix up this normal line a little bit here. Yeah, it always happens. Okay. So the light ray comes in, it hits the water, and then it bends toward that normal line. So it bends inward, and that's the idea. That's the whole point. That's refraction. All right, refraction is the bending of light. And like I said, if it's going the opposite direction, so in this case it was going into the water, if we have the light ray coming out of the water, we just, the problem is I keep double clicking. So I'm going to draw this dotted line here. This is my normal line. It's my line to help me compare things. So if I have a light ray leaving the water like this, what's going to happen? Well, like I said, it's going to be going at a certain angle, and when it hits the air, that part that's in the air gets to go faster, and so it spins a little bit, it twists a little bit, or pivots a little bit. And so I'm going to exaggerate this a little bit, but basically, and there's math behind this. We could do all the math that we want to here. We could figure out all the angles. So this angle and this angle are going to be different. So this outgoing angle, first angle compared to the second angle, they're going to be different. So we're going to have a much wider angle. It's going to bend away. So I'm going to get that ruler out of the way so you can see what happens when, just to kind of repeat myself here. Refraction is the bending of light. Okay, in fact, bending of light. Now, how does it bend? It has to go from one material into another. It could go from air into glass, air into plastic. This is how glasses and contact lenses work. But or it could go like from cool air into hot air, which is why you see the shimmering in like the summer over a parking lot or over a grill. When there's like really hot air, it'll bend the light that way too. But the point is the light goes from one material to another. There's differences in the material. And so just as an example, when air goes from a thinner substance, a less dense substance like air, into a thicker, more dense substance like water, it's going to slow down a little bit. And so since it's coming at an angle, the part that hits first is going to slow down and twist the entire thing. And so it's going to bend inward when it goes from air to water, and it's going to bend outward when it goes from water to air. Okay, so I'll repeat that just to simplify it. It's going to bend inward when going from air into water, and it's going to bend outward when going from water into air. And the reason is because of that twisting or that bending. It just goes faster in air compared to water. All right. All right. You need to watch that part again, do it. Okay, especially that last like minute. So that's 5.2. I can qualitatively, in other words, without numbers, explain reflection and refraction. Okay, so no numbers involved. That's all there is to it. All right. 5.3. Relative energies, applications, and effects of the electromagnetic spectrum. So the speed of light is something you can write down. It's about 300 million meters per second, but that's something right off the notes you can just get. A light year, remember, it's just how far, it's a distance. Whoop. It's a distance. It's how far light can travel in a year. In fact, how far does light travel in a year in a vacuum in space? So how far will light travel in 60 seconds? Come to think of it, that might not be something that we need to worry about. So let's just get rid of that for now. How far light will travel? No. Wavelength, frequency? I don't think so. So don't worry about that one so much. So this one, number 10, is definitely good to know. Frequency decreases. What happens to the wavelength? So frequency is decreasing, getting smaller. In other words, you're on the hall, you're playing with those springs, and you don't have to make such a high frequency. You can make the lower frequency. You don't have to go so fast. So think about what happens when you go slower making those waves. So when you go slower, the distance between the waves increases. So in other words, you go from something like this to something like this. So as frequency decreases, wavelength can increase and vice versa. So make sure you know that. Why is that? Because speed stays the same. The speed of any wave If it's in the same medium, will stay the same. If the speed of light waves is always the speed of light. So make sure you can do this. You know the frequency, you know the speed of light from question number 7. So you should be able to calculate the wavelength, because V is equal to frequency times wavelength. Okay, number 12. Your best bet, honestly, is to go watch that song. The song is linked in the description. In the could probably put a link in the one in the PowerPoint here, or in the YouTube when I post this. But your best bet, honestly, I probably won't. Just go to the window and look for the link to that song, the electromagnetic spectrum song. It was the one sung by the person who has a lovely singing voice. Okay, you know the song I'm talking about. So do that, and then what type of wave is light? It's electromagnetic light, or electromagnetic wave. Okay, and then question 14, literally looks like I copy pasted it and forgot to delete it. So my bad there, sorry about that. That's the same question as what, 10, so same. I think word for word, yep. Not sure how that happened, sorry. And wait a second, and 15, okay, so I don't know how that happened, but I must have copy pasted the whole thing. Weird. All right, what are waves and what do they transport? That's like the key question for this whole unit. Is it, you know, there are disturbances, they transport energy, that's for sure. They're a chain reaction. There's a lot of ways you could describe a wave, but make sure you understand that. Okay, so that's essentially it. There's not really much more to go over here. So I'm gonna just put this back up. Maybe I could squeeze that up. No. You know what? I'm gonna put the equations up. Those equations are pretty easy to find. I'll put them up. They're on the OneNote. They're everywhere. So I'm gonna leave with this refraction. And you know what? Waves carry energy. That's kind of important. Like I said, tomorrow we'll make our note card. If you have any questions, I don't see any right now, but I think I'm going to wrap this up for the evening, and we will talk more tomorrow. So hopefully this was helpful to you, and study hard. Good night.